Hi everyone, I'm Dean.
I'm Adri.
And we couldn't find a South African podcast with enough tech and innovation conversations, so we created our own.
So today I'd like to welcome Jason Miskin, our colleague, to this month's podcast. We'll be touching on the topic of machine learning within the industry of plant operations. Specifically, we'll be talking about control interlocking for safety using machine vision techniques. So Jason's going to help us unpack that.
Yeah, and as always, you can catch us wherever you listen to your podcast. This whole episode is something I'm really excited for, and I hope you guys enjoy.
Thanks. Welcome, Jason.
Thank you. Thank you for having me.
I'm going to give you a bit of an introduction. Okay, so Jason has been working for Optimum for several years now. He's been through many roles within the consulting team. As it stands today, he is a senior lead consultant. Can you tell us a bit more about the type of work that you've been doing with Optimum in the different industries?
I guess I can talk about that for a couple of hours, but we don't have that much time.
It's not the podcast.
So at the moment, I'm focusing on work within the mining and manufacturing industry. What we do within these industries is make use of their historical data to improve future production and future operations. And so it can take the form of all sorts of things. It could be predictive maintenance, it could be advanced process control, also all sorts of kind of data-driven modeling.
So it's within this space that you and another colleague of ours, Duran Joffe, who's not here today, discovered an opportunity to do some of this data-driven modeling application.
Correct. Yeah.
Okay. So what was the goal of the project that we're going to be talking about today?
I first want to just give a shout out to Duran.
Please
I think
do.
he did most of the technical work. He was the lead data scientist on this.
One of our bright sparks in Optimum.
Yeah.
Sure.
So the goal of this particular project was to improve the safety of people and equipment within quite a dangerous operation. And so what we set out to do was make use of machine vision techniques to pick up on hazardous condition and notify the right people in order to prevent accidents from happening.
So when you say operations, what kind of operation is this?
So this, in this particular case, it was a furnace operation. Yeah. Should I explain what a furnace is? So a furnace is basically a big piece of equipment that is used to separate material. It is used to separate valuable material from waste material, and it is fed ore, which is effectively solid material that contains a lot of valuable materials, but it needs to be refined further. And so what happens is this ore is fed into this furnace together with all sorts of other reagents and air and all sorts of things. It is melted. So you can now imagine the temperature of this furnace. It's sitting at about 1,200, 300 degrees.
Right next to a volcano then.
It is literally pretty much a volcano.
Indoors volcano work.
Yeah.
Gotcha.
Yeah. And so once this ore is melted, together with the reagents, it actually separates and creates two different phases called the matte and the slag phase. The matte is the waste material. Sorry, the matte is the valuable material, okay, and the slag is the waste material. And so you can imagine it as water and oil. If you mix water and oil and you let it settle, you'll see that it creates two phases.
So matte is the water in this instance?
Matte is the water in this instance. As slag. It settles to the bottom, slag goes to the top. Okay. And these two different phases are tapped out so that they can be processed further.
So within this particular project that we did, I can imagine furnaces could be in several different types of mining operations, for instance. Where was this specifically? Is this like a gold thing or a platinum thing?
You'll find furnaces in all sorts of refinements, in all sorts of different valuable material processes. In this particular one, we're looking at a platinum group metals process, so PGMs for short.
Okay. So you mentioned that the aim of the project with the client was to improve safety conditions. What kind of results would we be looking for to reduce the risk that I believe operators are at within the furnace operations?
So I guess for this particular client and this particular site, there have been a number of incidents where there was eruptions of the furnace, so molten material flying out of the furnace, and this poses a big hazard for both people and equipment. So yeah, it's quite important to try and prevent those incidents from turning into anything more. And so there was this, a couple of it happening, and there was this drive to improve safety. Safety is a very important thing within this industry in general. There's a lot of risk factors in the industry, and most companies focus on safety of their people and equipment.
So this is where the technology of machine vision comes in.
Yes, yeah. So I guess the reason why we're looking at machine vision is in this particular process, you can, if you just visually inspect the footage, you can see leading indicators evolving prior to an incident happening. What that means is, as a human, you'll be able to see, okay, well, in this scenario, there's a lot of excessive amount of steam being generated around the furnace. And so what we are trying to do with this machine vision, and what we have done, is as opposed to a person having monitoring the screen constantly, you replace that with an algorithm that would be able to effectively pick up on the same things a human would, but would be a lot more focused.
So just quickly to touch on the leading indicators, you mentioned excessive steam. I'm assuming that's one of those leading indicators.
Correct.
What other indicators are we looking at, or what other indicators is the algorithm as well as the operators? What are they looking for?
So with the purposes of identifying dangerous conditions, steam is the only leading indicator we're looking at the moment.
Okay.
But the algorithm that we've built is quite versatile. It can pick up anything that you effectively tell it to pick up. And we wanted to not only identify steam, we also wanted to identify people walking around on the tapping floor, as well as the mud gun, which is the thing that goes and plugs the tap holes. That's the place where the molten material is taken out of. When we do detect steam, we also want to detect and differentiate between different types of steams. So this process inherently has a lot of steam being generated, and some of which are normal, some of which aren't. And so it was very important that our algorithm is able to identify what we call light steam, which is a steam that is normal, and then heavy steam, which is a steam that is in excess and is leading us to believe that there's something amiss.
Something going wrong.
Yeah.
Down the line, if that excessive steam keeps coming up over time, something bad is going to happen.
Yes.
Like the incident that you mentioned. Okay.
Correct, yeah.
You also mentioned people being on the floor.
Yeah.
I'm visualizing operators standing behind certain equipment with screens, monitoring the process, what's happening in that refinement space. When you're saying people on the floor, are these people on the floor where maybe they shouldn't be?
Yeah, that happens quite a lot. So the tapping floor is quite open, and in certain cases, you actually need an operator to go and manually lance the hole, meaning that it might be stuck, it might be clogged, and then you need a person in there. But in general, that floor should be clear because it is a dangerous area. And so there's no physical barricade that keeps people out because there actually needs to be people sometimes there. But for the most part, it should be clear.
So I'm seeing two types of safety measures here. It's sort of the technological safety measure where we've got not just human operators monitoring the system, looking for these indicators, excessive steam, but there are people in places where they might not necessarily, should not necessarily be at certain points in time.
Yeah.
And so an algorithm like this, depending on how we've built it, and we'll get into that.
Yes.
It can actually cross a lot of T's, dot a lot of I's, lots of birds out of the sky with one stone, if I can put it that way. Okay, so there's a lot to gain, depending on how we've built it and the success of that algorithm and how we've adopted it.
Yeah.
Should we dive into that then? Like, how did
we
do
can
this?
leave it for later, but it's worth mentioning that we built the algorithm to detect all sorts of different steams, but then also the mud gun and people. Okay. And so the fact that we're able to detect people gives us an opportunity to do more than just identifying leading indicators. And we can touch on that.
Expanded the brief in that way.
Exactly.
Okay.
Yeah.
A really nice outcome.
Yeah.
Instead of the other outcomes that we sometimes get through projects. Okay, so let's talk about it. Let's dive into it. Let's get a little bit technical here. How did we start with this algorithm? We've used words like machine vision. I know in the title of the episode we're saying power to sight. Yeah. I also mentioned in the introduction something about interlocking, control. Let's simplify it. Let's bring it down to one way that we want to describe it.
Yeah.
So we're saying a machine vision algorithm as an application to enable operators to operate these places more safely.
Yeah.
Reduce risk. What is that machine vision algorithm? How did we start? Where did we start?
So it's quite loaded. There's a lot happening with this algorithm. Maybe just to touch on the reason why this is actually useful. So, like I said, a person can identify these leading indicators, and so a question might be, okay, well, why don't we leave it there? The reason is operators sit in a control room. There are hundreds of screens all over there, like around them, including a video feed of the tapping floor. But that's not their primary job, is to stare at a video feed and
just one.
Yeah, exactly.
The whole time.
They are literally controlling this entire process. And so they've got all sorts of higher priorities. It's worth also pointing out that these events happen quite infrequently. So
the excessive steam coming out. Okay.
Let's say it happens once every 6 months. Can't expect a person to sit and stare at a screen for 6 months just for that one
grow old doing that
occasion.
Yeah.
Over and above that, you can develop the algorithm to monitor this 24/7, right? And have an operator focus on the things that he needs to focus on, or she, that is more important for their role. Furthermore, when you build an algorithm like this, you're able to identify these events a lot sooner, because this machine vision algorithm is constantly looking, and as soon as there's something amiss, it would do what it needs to do. So just to kind of touch on the reason why we wanted to do this in the first place, in terms of how we tackled it, there's a lot.
There's a lot. I want to loop us into it, but I want to bring to the front something we hadn't discussed before, and we don't have to talk about it, but it's interesting to hear. We're going to cover, this machine vision algorithm. It lives, from my understanding, in the machine learning world. So there's AI here that's happening. This is a really great example of AI enabling human safety, enabling workplace safety environment, enabling operators to perform at a much better level within their own roles, within their jobs, maybe to a certain extent actually reducing stress around what you're doing every day as an operator. Whereas AI, when we talk about it and jobs and what it could do really well, which obviously we want this AI to do really, really, really well, has to do the job well and has to do it right all of the time. But it's a good thing in this instance. It's not replacing someone's job. It's not taking away from someone's role or their performance.
Yeah, it's supposed to bolster their
Yeah.
role. So this is one thing that happens very infrequently that they don't have to worry about. They will get notified when something happens, and then they can just change their view and look at the screen and see what's happening.
Okay.
And so it reduces stress, and it allows them to focus on the thing that they are there to do.
Additionally, there's the entire business angle to this. It just makes a lot of sense for the business that is running this operation to reduce any risk in any way, whether it's to equipment, whether it's to actual human beings that we're calling operators, the output of their material. It's a big business value to this. But for me, more importantly, I think it touches realistically on AI isn't replacing all of the jobs in the world everywhere. We can find places, opportunities where it's enabling what we need to do as human beings.
Correct, yeah.
So, okay, so let's talk about the machine vision algorithm, the application. We always have to start with data. So I'm assuming to get you going, I'm pretty sure that we jumped into this with the data.
Yeah.
Data handling, data labeling.
Correct.
Go for it.
So, yeah, it's exactly that. We had to take a lot of data, a lot of video footage. That's our data
video
source.
footage. Yeah.
Video footage, historical video footage. And we had to find and define what is normal and abnormal conditions. A normal condition would be a process where there is no steam generation, it's just operating and there's nothing to see. Abnormal days are when there's something of interest in the field of view of the camera that is worth noting. This includes the light steam, the dangerous steam, which is the heavy steam, people, mud gun, and so forth. For the days that we have abnormalities, we had to identify where those abnormalities are. So our algorithm doesn't only say that there is something or there isn't, it also identifies where exactly in the image this is happening.
Okay.
So we used certain apps to make that process faster, because we can't go and label every single image in, let's say a year's worth of video footage. That's not going to work. So it was a semi-automated process where you start labeling a couple of things. You build a model that takes that information, and then it goes and predicts for the rest of the footage if there's anything of interest. And as it predicts, you correct it, and then you train it on the next labeled set. And so it's this kind of compounding effect of semi-automation of the training process.
How is the algorithm actually measuring the steam? I can visualize how the algorithm is trained to identify a person. There's quite a lot of networks out there for that. But steam is quite unique. I wouldn't know where to start. How do I measure the amount of steam in my bathroom? Did I have a light steam shower or an excessive steam shower?
Yeah. So we work closely with subject matter experts, SMEs for short. These are the experts on the ground that know the process in and out. And we had to figure out with them what we need to say is light steam and what we need to say is heavy steam. And there you can, if you visually inspect the footage, you'll be able to see, okay, well, this light steam isn't that dense. It's quite sparse, and heavy and dense steam is a lot thicker. And so we had to tell and label our data such that the algorithm can also distinguish between them. But we also don't want our machine vision algorithm to take action or raise an alarm or whatever the case may be every single time there's some dense steam. There also needs to be some sort of threshold, which the amount of steam to cross before there's any action being taken. Otherwise, you'll have a lot of false alarms.
So if there's excessive steam for a really, 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 really short amount of time, is that the appropriate threshold for this algorithm to raise an alarm, or should we have told it to wait?
Yeah, exactly.
A little bit longer. Yeah. Okay.
So that's where we also worked with SMEs, and we set our threshold. So the algorithm would not only identify the steam, but it will keep track of how much steam has been generated, the density of the steam, and all sorts of things like that. And then based on these thresholds, it would decide what action it needs to take.
Okay, so the way that we've trained this algorithm, we could even call it the models that have been used.
Yes.
Is this machine learning? It's in the world of AI. Could we be a bit more precise?
Yeah, it is. It is machine learning. We ended up using a deep learning.
A neural network.
A neural network,
Okay.
deep neural network, namely a YOLO V4 network, which is you only look once. It's a single shot object detector, meaning that it can identify multiple things in an image at the same time without having to run through the things that it needs to detect. Before we got to that final solution, there were a number of other things.
I was going to ask. What else did we try? How did we land up on YOLO? Why YOLO?
So
for this one,
we always try and make our solution as simple as possible for the problem at hand. So if there's something a lot simpler that can do the job to metrics that we've predefined, we'll go with that. Simple is always better, but not always better if you can't do the job properly, right? So we did a couple of things. We tried to do motion detection first, where we basically just checked whether there's anything moving on camera, and we basically said there's something moving on camera. Problem with that is that there's a lot of other things moving on the camera, not only steam.
I was just about to say, people, I mean, like the people, closing the tap holes,
all sorts
of things. Fly buzzing past because it exists there. Okay, all right.
After that, we looked at color segmentation. So we tried to see where the color of the steam, we can use the color of the steam to both identify that there's steam in the image, but also distinguish between light and heavy steam. It was able to identify steam, but it couldn't distinguish between light and heavy steam, which was crucial for us. Otherwise, again, a lot of false positives, false alarms and so forth.
Okay.
And then lastly, before we went to deep learning, we looked at velocity flow vectors. So the thinking was steam moves in a very certain way, and there aren't a lot of things that move in that image in the same way. The thinking is that as you have steam moving through your footage, you identify points of interest within the steam and you see how that moves between images. And based on the flow vector of the steam, you'll be able to say this is steam or not. That worked pretty well. I think the challenge there was when the steam gets very aggressive, then it starts moving in all sorts of other directions. It becomes quite turbulent.
Yeah.
And it was always worth considering all these different simpler solutions. But then at that point, we went to deep learning.
Okay. So once the algorithm has detected excessive steam within the thresholds that we've qualified with SMEs, and it's done this successfully, what's happening? I know we've mentioned some things like alarms, for instance.
Yeah.
So what are the different things that this application is doing alongside the operator, or when the operator isn't viewing the video footage?
Yeah.
How did the operator actually know? How did we know on record that this was identified successfully?
So it's a very good question. So when you build these type of algorithms, and the intent of that is never to sit in a back room and it's never used. The intention is always to build it such that it is adopted by the end users. In this case, the end users would be the operators for the most part. And so the question becomes, how do you expose this to operators that would make most sense? How much authority do you give an algorithm like this so that it actually has an impact? We decided to have multiple points of exposure. The first one was having our algorithms output, which is original video footage with our bounding boxes and all sorts of information overlaid with it to write that into their existing surveillance system.
Okay, so they use an existing surveillance system, the operators.
Yeah.
And there's a layer on top of that with the specific video feed where the algorithm is drawing these boundaries. I mean, you see it on social media. You can like look on an Insta reel or TikTok or whatever. And there could be like a video stream that's being captured and is in order to identify people, dogs or cats
Correct.
or trees. There's a boundary box and it's colored.
Yeah.
Okay.
So it was effectively what we call a virtual camera.
Right.
For the operator's intent, it is a camera just with extra information on it. And the beauty of it is they already know how to use their surveillance system. They know how to rewind, download, and watch the real-time footage and switch between cameras and all those type of things. So we got that for free, basically, because our camera just becomes another camera.
Yeah. More informative.
More informative, though.
Okay.
That's one piece. But that's not the only thing that you can do with an algorithm like this, because otherwise you're running into the same issue. The operator is only looking at the screen once every hour, let's say. It's also worth mentioning that these leading indicators, these occurrences of steam, are very fleeting. They happen and they disappear, and it's you can't expect a person to.
You could
pick
blink.
Yeah, you could blink and it's gone.
You could look at the other monitor for 3 minutes, come back, and you would have missed it.
Yeah, so this virtual camera isn't the only thing that we had to do here. The other integration was to connect it to their SCADA system and their alarm systems. So once that threshold is crossed, there's an alarm that's raised. This is something that an operator can hear, and they need to acknowledge the alarm. In this process, they can then go and look at the screen and see what's actually happening and look at our bounding boxes and see whether it's worthwhile. That in itself is already valuable, because now you're only drawing the attention of the operator to the screen when it's actually necessary. And lastly, the last point of kind of integration is automated intervention.
Okay.
So at some point, when the risks of excessive steam, and it becomes quite heavy and quite big and dangerous, we can automatically take intervention and take necessary steps to be able to reduce the risk and stop it in its tracks. The automated action here is to take the mud gun and close the tap holes. And this is also something that you can give to the algorithm.
Okay.
This is only in very extreme cases. Typically, you'll have an operator take action, but when it escalates so quickly and your operator might not even have time for it, you can have this algorithm do it as quickly as it can.
So it could be a matter of seconds.
It could be a matter of seconds.
And just bringing back into the loop again, that aspect of someone could be on the floor, this incident could be rising, it could be starting.
Yeah.
So that automated intervention could essentially save a life, but it could also expedite a process that the operator just didn't have those couple of seconds for. As you mentioned, this takes place in seconds, not half an hour, a minute.
It can play out over a very long time, over quite a period. We can talk about that a bit later, but it could also be quick.
Okay.
And you might find that an operator had to leave the control room to go and do something on site. And in those cases, for example, you would want to ensure that there's a fallback.
Yeah.
So that this can.
And so that's all that this automated intervention is at this point. It's a fallback. It's literally the last option.
Correct.
If the human being is not around.
Yes.
And so let's talk about that integration a little bit more, because I know it also leads us to how do we know that this is going to continue working well in the future. So we essentially have given the algorithm permission where it's now sitting. And that permission is very narrow, very specific to what the algorithm can ask other equipment to do.
Yes, there's one thing it can do.
Yeah.
It can go and move the mud gun and close the tap holes. That's all it can do. And it can raise an alarm.
And so if it does this incorrectly, if the algorithm isn't working as it should, it incorrectly identified excess steam to the point where it wants to take this automated action. It's not necessarily a big deal in terms of safety and risk at that point. It's okay if we close those tap holes for a little bit.
Yeah.
The important thing is that the people are safe in the
Yes.
scenario. I know there's a business angle to
the
this.
business angle
There's
is
always
very important.
Yeah,
it's
there's always
incredibly
a business
important,
angle.
and it can't be put to the side because these guys have a job to do. They need to produce a certain amount of materials every day, and any interruption in that, unnecessary interruption, is not good. And so the algorithms acting on false positives is unacceptable, and it shouldn't. This machine vision algorithm is extremely robust because it uses this incredible neural network to identify steam in every image. And we count the number of identifications in every image at a certain frames per second. And then over a minute period, we keep track of how much steam has been generated over a minute. And so even if there has been a false positive in a single image, that gets smoothed out by all the other correct counting it's been doing.
So there's accuracy and speed in this.
Yeah, accuracy and speed comes
That's the
into
trade-off,
it.
right?
Yeah. But my point is that the algorithm is built in such a way that it actually doesn't produce false positives anymore. It's been an iterative process, and we can talk about that in a bit. But and this is one of the requirements of this: is it needs to identify dangerous conditions, but it should also not produce false positives.
Okay.
Because those two things are very important. It can't be an algorithm that identifies all the dangerous conditions, but then also have the same amount of false positives, because then that will just cause a lot of issues.
It's high stakes game.
It
Very
is.
narrow window to work within. Okay.
Yeah.
So I mean,
Hey guys, we really hope you enjoyed what you've heard so far in the conversation between Adri and Jason on Safety Insight and the Control Interlocking project that he worked on. When we recorded this, we saw that this was going to be much longer than the half an hour episode we had planned for. So we've decided here to stop it for part one of the episode. What that means is next Thursday there'll be a special part two kind of episode, a new episode in the launch of Across the Opti-Verse. Please look out for it, and remember, you can catch us wherever you get your podcasts on, and we hope to see you back next week. Thanks so much.